Okay, so next up we've got Ian Fairchild talking about Speleothem science.
Thank you, Gina, and thank you to John and Andy for the invitation. So, the term Speleothem, that was around 50 years ago. It was introduced by George Moore back in 1952, and it comes from the Greek. Speleon, meaning cave, and thema, meaning deposit. I carefully pointed this out to a colleague from the sports science department at our university who was interested in physiology underground. He said, I know, he said, I am Greek. So, Speleothem Science is also the title of a book I published with Andy Baker a little while ago. And so we're going to explore some of the ideas that are there in that book. The first 10 pages of the book are actually worth reading. But then after that, you've got to be a research student to get into the detail of it all. So I'm going to dance lightly over these few topics here. The reason that there's so much interest in the scientific literature generally about Speleothems, particularly stalagmites, is that they've proved to be a wonderful way of investigating climate over the last 500,000 years or so. So I'm going to start by just pointing out who the competitors are and why Speleothems have risen to challenge the previously dominant archives of climate. And then we'll look at one or two sort of concepts, abstract ideas about how Speleothem form and how do they keep going. And then the idea that they record an environmental signal that's transmitted down from the surface and encoded within the properties that these Speleothem display. One of the amazing things about this Speleothem is you can home in on what goes on within a given year. On the other hand, you can look at things that happen over up to periods of up to hundreds of thousands of years. So the dynamic range is quite extraordinary in these deposits. So we'll explore that in those a few slides on 4 and 5. And then one or two examples of environmental histories. And then finally, just a word about Speleothems. Do they record the Anthropocene, the current epoch where humans have significantly modified the planet? Well, this diagram was, the original version of it was made famous by the Intergovernmental Panel on Climate Change in their reports about climate science. And we've just subverted it here by just putting a few caves into the system. And the reason we've done this is to show that they are there, they're listening. They're listening to what's going on in the external environment. Now, this diagram was drawn to refer to climate, but actually Speleothems record more broadly the environment as it changes, both the climatic factors, but also factors like the vegetation at the surface. Now then, these rival methods of obtaining information about the past. Well, but from the 1950s onwards, there were these amazing studies from cores in the deep oceans and the records of calcareous plankton, like those you can see in the photograph there, that are preserved within them. And those records gave rise to this amazing story of climatic fluctuation. This diagram shows us from 5 million years through to the present day. And so we get from this the idea that the amount of ice in the world decreased and increased. That is, we have interglacials and glacial periods. And this information is encoded in the oxygen isotope composition of these calcareous fossils, a proxy that we also use when we talk about when we look at Speleothems. But the great thing is that this pattern, the complexity of this pattern, is beautifully revealed by these studies. Now, another great archive, of course, are ice cores, and here we've got Dorthe Dahl Jensen having drilled this neem core, and this is the very bottom of the neem core, some 3 kilometers below the surface of the ice sheet. So as snow accumulates and is compressed and forms ice, if you drill in the right place, you get a beautiful record about what goes on. If you drill in the wrong place, you get all kinds of folds and things like that. Now, what these deposits have been able to show is not only a history of the atmosphere preserved in cave bubbles, but also a very, very intricate history of the fluctuations in climate. And here we've got some fluctuations of climate between 20 and 80,000 years ago. That is during the last ice age. So they're homing in a lot more detail about the conditions at that time. Now, a problem with both of these methods is that you cannot date these deposits directly. At least you can do carbon dating on the ocean cores, but that only goes back a few tens of thousands of years. So all kinds of tricks are used to get an absolute age on these deposits. You have to dodge and weave to get the best estimates. So what was needed was an archive that you could date in an absolute sense, and this is where Speleothems have come to the fore. The other thing about those deposits, of course, is they occur in places where humans don't live. So if you go on land and say, well, what have we got on land? And the trouble is that on land, mostly, we've got deposits that are fragmentary and only record short intervals of time during these intervals of glacials and interglacials. Whereas Speleothems can grow for longer periods of time and therefore give you more continuous records. But people, for a long time, many scientists, particularly climate scientists, wouldn't go near them. Partly because they didn't want to go into caves, probably, but partly also because they were just horrified by how complicated everything looked. But, of course, once you start getting your eye in, the complications become a little bit clearer. I mean, we've got a stalagmite that has been broken and felled. Was that human action? Was it an earthquake? It could be either, depending on the circumstances. And then new growth has occurred afterwards. Just because we have stalagmites next to each other doesn't mean that they grew at the same time. This is a very fresh young one. That's a much older one. But these two are like a pair. You see the way that they dance together. And so they're probably forming from a similar drip. Here we've got one from southwestern Australia. The forecast here is that things are going to get a lot drier in the coming decades. Actually, it's already happened over the last 20 years. It hasn't got drier. And a drip that used to form a growth across the whole of that surface is now only feeding growth near the center of that stalagmite. So the gross morphology of stalagmites can tell us about the conditions and how they've changed over time. Many of the other ways in which we study them involve looking at the rate at which they grow upwards or their chemical properties. And by using a combination of these, what we call a multi-proxy approach, we can end up understanding how things have changed over time. So when thinking in the most general way about Speleothem growth, then, we have to concept about, well, how is it they grow at all, and what do they need? And so there are a couple of metaphors here. One of them is the idea of the Speleothem factory, the idea that they're being created and they need a supply of ingredients which are delivered to the factory and pass through the factory gates and down into the place where the stalagmites are being formed. The other concept, which Andy Baker came up with, was the idea of the Speleothem incubator. I mean, it is quite extraordinary to think of it that these structures can grow for periods of up to hundreds of thousands of years, drip by drip, growing at rates of sometimes a tiny fraction of a millimeter per year up to about a millimeter per year. And to keep that going, to sustain that, and those very slow, continuous rates, match anything that humans can do, but over very, very long periods of time. So the idea that you have to maintain these conditions is, caves are really quite extraordinary incubators. And this happens because of the very steady rate of dripping water supply that can occur, at least in some cases, and also the way in which caves ventilate, the way in which the product of the calcium carbonate forming reaction, that is CO2, is removed by cave ventilation, allowing the reaction to continue at a more or less steady rate. So from this, then, we get the idea of caves having a physiology. We know the idea of Gaia, the planet has a physiology, we each have a physiology, and caves have physiology. They have an exchange of heat, of water, and of gas, which allows them to sustain that pattern. And so they are capable, then, of recording an environmental signal that passes into the cave. So here we've got above ground, we'll have, let's say these are annual rhythms of change. and that's a signal that passes down into the subsurface. Or there may be something, some disturbance, maybe a forest is cleared overhead a cave, and that causes some longer-term change that gradually recovers. Either of those kind of signals can pass down through the chemistry of the soil water and the amount of soil water into the karstic aquifer, where the chemistry of the water is modified, and then modified again when the calcium carbonate precipitates. And then we end up with a speleothem. And if we drill through our speleothem and get the record of change, sometimes we see a very intricate, detailed record, and sometimes we just see a very, very gentle change. So sometimes we can recall the details, sometimes we can only see the longer-term changes, depending on exactly which speleothem forms. So we see that they really are complicated, but on the other hand, if you collect different samples, you can look at features on different scales. So what Speleothem scientists try and do then is to go from this and use what's technically called a transfer function to go back to the original information. What is this telling us about rainfall, for example, in the past? So we first really tried to conceptualize this whole business back in 2006, and this paper actually turns out to be one of the top 10 published papers in terms of citation in the year 2006 in geology, which illustrates the interest that there has been in this subject from climate scientists more generally in recent years. And the idea is that if you've got, if you look at the properties that Speleothem shows, some of them directly reflect what's going on in the atmosphere. And you almost don't need a transfer function. It directly tells you how that atmosphere composition is changing, whether it's radiocarbon in the atmosphere or whether it's the oxygen isotope composition of the rainfall. In many cases, though, there are modifications as the water passes through the soil, and there may be a soil signal that you see. In other cases, it's due to the degassing of the water in the cave, and that in turn may be an indirect reflection of how dry or wet conditions are. So if any of those things apply, then we can use this transfer function approach and get back to the signal. However, there are other things that happen as the crystals grow. All kinds of weird things happen to do with the way in which that growth happens. And there may also be secondary changes as well. So we can't always interpret the original conditions depending on how well preserved the Speleothem is. So thinking about how that signal is transmitted down into the cave then, the soil zone is really important, and the high carbon dioxide levels in that soil lead to a lot of dissolution of calcium carbonate and give us the potential. And the more that happens, the more Speleothem growth can happen in the cave underneath. And then looking on a bigger scale, we see them sort of at the surface, and then, of course, all kinds of fracture networks. And there's a cave in that big quarry there where this Speleothem can form. The way in which water passes through the karstic network, of course, is incredibly variable. And whereas for most purposes, most cavers, of course, are interested in the crucial problem about, will a cave flood and thinking about the big water flows. And here, ironically, we're looking at the really tiny water flows, just drip by drip, or in the case of flow stones, just intermittent, larger flows. And so the water may be flowing along a simple flow line, or it may be stored for a period of time. And the different hydrologies give rise to different properties of the stalagmite. So one approach that we can take is to think of the karstic system as like a plumbing system, and you can have these different ways in which water will pass through. The matrix is a bit like a sponge, and the fracture is a bit like a crack, and the conduit is essentially like a pipe. And we can have different combinations of flow representing these the different parts of the karstic aquifer. And it's been realized that actually one really important control on the composition of the precipitates is something that's often abbreviated to PCP, referring to prior calcite precipitation. What that means is what happens before, on the flow line, before that water reaches the stalagmite of interest. And this was an idea that was put out there about 50 years ago, in fact, by a very famous geochemist, Dick Holland. But then it was kind of forgotten. There's many ideas, actually, were there by some pioneers and then forgotten for for decades. And then we started to resurrect it. And then Alan Matthews, looking at isotopes, to resurrecting this idea as an important control on Speleothem composition. So the idea is that if there's more calcium carbonate precipitation in a stalactite or in a chamber above the cave that you're looking at, then the more the composition of the water will be modified, and you can actually interpret that modified signal in the stalagmite itself. So we end up with this idea then that you've got a zone where the potential for stalagmite formation is generated in the soil, where the CO2 pressure is very high and lots of ions are dissolved in the water. And then as that water percolates down into the cave, it encounters a gas phase, an air, which has a lower CO2 pressure than the soil, or sometimes the subsoil, with which it's encountered the highest pressure of CO2. And that degassing of CO2 then permits calcium carbonate to form. And it's a really crucial thing. So the nature of the ventilation in the cave then is a very strong control on how much calcium carbonate can form. So let's have a look at some of these properties that they display then. And one of them is just simply the rate at which they grow. And if there are any young Earth creationists in the audience, well, I mean, one of the things that one can do is to say, take a bottle. There's a bottle that's been sectioned. Put that bottle in a cave. This one's in France. And just leave it there for 20 years. Take the bottle out, slice it, and there we've got 20 years of growth. We can see these layers, and we can prove that they are annual layers. And you then say, right, then, now look at your stalagmite that's this high, and look at the layers, they're the same layers, and count them. So it's a tremendously simple way of demonstrating the nature of the passage of time. So the rate at which they grow then, which is shown here, that's in fraction, that's up to 1 millimetre per year at the top. That will depend on temperature under conditions where there's sufficient water to allow CO2 to build up in the soil. So warmer soil, other things being equal, will generate more CO2, and will therefore, that water, when it percolates into the cave, will degas more and allow faster growth. So there is a relationship to temperature, but there's also a relationship to the amount of water as well. And then if we look at the gross morphology of a stalagmite, here shown in section, if there's less water availability, you'll have a narrower stalagmite. With more water availability, it'll be wider and also tend to be more conical in shape. So growth rate is one of the things that can be a proxy for climate, for example, the amount of rainfall. This is a small cave which wouldn't count much in John's statistics. It's only about 100 meters long, and so it would be there as a footnote. But it's been a tremendous natural laboratory for studying the way in which speleothems form and respond to external conditions. And we've done quite a few studies there using different parameters for the first time. And so it's based in Mesozoic limestones and dolomites in the Brenta dolomites in northeast Italy. Now, one really striking thing about the deposits in this cave is that their rate at which they grow is very sensitive to temperature. Now, if you think back to the 19th century, not many of us were around then, but in the mid-19th century, that was the end of the Little Ice Age, and conditions started warming up in Europe. And this is very sensitively recorded by these stalagmites and stalactites. So here we've got annual layers in a cross-section through a thin section of a stalagmite. You can see how the growth rate increases dramatically, and this is about the mid-19th century. And similarly, this is a stalactite, a tiny straw stalactite that's been sectioned. And these are little ridges on the wall of that straw, and you can see how they're very thin there, and they get thicker here. So that's reflecting the same time period. So sometimes, if you've got the right cave and you've got the right sensitivity, the growth rate can be a proxy for temperature. In other cases, it's a proxy for rainfall. Now, those layers I showed you also have another very interesting property. They fluoresce if you put them under ultraviolet light. These are examples here, these subhorizontal bands. And these are two other examples from completely different sites. This one's from China, and this one from Austria. And these fluorescent bands, they fluoresce because there are fluorescent humic substances, humus, washed down from the soil and incorporated as very tiny amounts of these organic molecules inside the stalagmite. And what's even more extraordinary is that this fluorescent organic matter takes with it certain chemical elements. So there are the bands in section, and there's associated with them, there are enrichments in certain metals. And this can be summarized on this diagram, and it shows us the average enrichment of various different elements across the layer. And these are all elements like lead and copper and phosphorus, which like to associate with these organic molecules. So we've got a signal of the flushing of soil material into the cave here. And you can see how it's much more important during this period, where the layers are very dark and these trace element levels are very high. And this corresponds to a period in the First World War when the forest was cut down for the war effort at the time. And that is then reflected in the Speleothem properties. And an even more spectacular example, this is from a cave in Austria where there are lead and zinc deposits in the overlying limestone. And you get these enrichments in lead and zinc, which can be picked at very, very sensitively by particular chemical and analytical techniques. And so that's a single year. This is the year 1978, when I first finished my initial studies. And in that year, in fact, I got a degree awarded that summer. And I think you can then say, well, look at each of these bands. There are lots and lots of these bands. They reflect water infiltrating into the cave, and there are lots of them within one season. So in this case, this is like the ultimate resolution that's ever been found in a stalagmite. Synoptic rainfall events of just a few days' duration are actually preserved in that particular sample. Another, I think, a really beautiful example of the degree to which the detail can be preserved is this example, which is from James Baldini's group in Durham. And James is talking later about monitoring caves. And what we're seeing here is a very, very detailed record of the carbon isotope variation in stalagmites. And that's actually telling us about the processes, the dissolution processes and the degassing processes that are going on in the cave. And the long and short of it is that you have a dry season and a wet season, D and W, and you can see that annual progression. And you can see how dry is the dry season, how wet is the wet season. And follow that through, and here we're going through from 1780 to 1820 AD, and looking at the pattern in different years, and they're able to interpret that pattern in terms of different amounts of rainfall, in terms of how the big picture, this is the intertropical convergence zone, that's a big climatic control on rainfall, and see how that varies from year to year. So high resolution events, fantastic stuff that can't be obtained by other means. But you can also, of course, look at very long time periods, and you can get absolute ages, which is the way that stalagmites score over ice cores and marine deposits. And the most common way in which this is done is to look at the amounts of uranium-234 and thorium-230. And as over time, the amount of thorium-230 builds up in a stalagmite. There isn't any thorium in the original deposit, but it builds up over time. And so we can use that to date the Speleothem. So we can date Speleothems this way. We cannot date marine fossils this way, because there isn't enough uranium in them. And I was lucky enough to be in this guy's laboratory on the day that his paper in Science was published in 2009, and where the errors, basically he was boasting that the errors had been reduced by a factor of 10 in their latest technique. So this step that we see here, around 130,000 years ago, this step in oxygen isotope composition corresponds to a warming, and he was able to show that this warming was happening within a period of a few decades using this dating technique. So nothing like that can be obtained by other techniques. It's a really fantastic record. And then if you look at the longer term record from caves in China in particular, where there are some fantastic records. This is a composite record stacking together caves. So this, in the red box here, this is the record of oxygen isotopes going back 600,000 years, compiled from different caves in China. And it can be argued that this is the definitive record of climate change over the last 600,000 years. It tells us about the monsoon history, and the monsoon, it turns out, is a great integrator of the global state of climate. So that's so Speleothems have really proved their worth, and each one of these fluctuations can be matched with fluctuations in other archives. So in the lower parts, we've got archives from we've got records from ice cores, and which are not so well dated, but we can, by correlating the fluctuations, we can date when these things occur using the Speleothems as our primary record. Well, do you know that feeling? I don't know, some of you are slightly older than others, but here's Lisa, and it was 10 years since Lisa had been and finished her PhD fieldwork in Tartare Cave in northwest Scotland, and she's still fitted in her caving suit. That's why she's so pleased. Here's some lovely records from these slow-growing stalagmites in northwest Scotland. It turns out that the rate at which they grow is an inverse relationship to how wet it is. And Andy Baker and Chris Proctor ended up with this fantastic record showing how those variations went with time. And they were an exact mirror image of the rate at which trees grow in Morocco. And it's because of something called the North Atlantic Oscillation, and which controls how dry and cold things are in Britain in the winter, and conversely in southwest Europe. So that was a lovely record. It comes from British sites. This is Emily Macmillan, who's been working on stalagmites from southern France and looking at a dry period, again using this idea of prior calcite precipitation and demonstrating a dry period about 1,200 years ago that corresponds with the time when the Mayan civilization retrenched in the Yucatan Peninsula in Mexico. And here, yet another completely different example. This is using organic molecules in stalagmites to tell us about changes from natural vegetation to farming, and here during the middle of the 20th century. And there's a great scope in future to use these organic biomarkers. Are we now living in the Anthropocene? Have we left the Holocene behind that we've had since the last ice age? Have we now moved into a different epoch? Arguably we have. The next ice age has already been cancelled. We can't, we've already put too much CO2 in the atmosphere to delay the next ice age. And this is because of something called the Great Acceleration, where our rate of use of all kinds of things has increased, and the rate of CO2 addition to the atmosphere has been enormous. So do stalagmites record the Anthropocene? Well, they do in the sense that we've got an increase in radiocarbon from atmospheric nuclear tests. That's preserved inside stalagmites. We also have pollution records. So here in that Ernesto cave again, the Speleothems recording increased sulfate from burning of fossil fuels with sulfur in them, in the same way that trees do as well. So there are things going on that we've changed the environment, and they are now being recorded in Speleothem. So Speleothem Science was our book. It was nice and polished by the end. This is how it started. 10 chapters of scribble. In the end, we had actually 12 chapters, because we realized there were some quite important things that control Speleothems that we hadn't included. So, as I say, the first 10 pages, great stuff, worth looking at. Now, if you forget the key, then, of course, you've got to go under the gate, which is Bartolome Andreu here. This chamber, a stalagmite had been broken by vandals, and but nevertheless, he still wanted to take it, even though he had to give a lecture in 2 hours' time and his university 40 miles away. So he made it just about. But this stalagmite turned out to be too complicated to use in our work. So eventually, we decided it would be the ideal sample to use for an exhibit in the Science Museum. And this is an exhibition called Atmosphere, which is all about climates and paleoclimates. And so there is a stalagmite, a Speleothem presence there, and this sample has been very nicely mounted. And originally, it was due to be on for 5 years, but it's actually extended till to 2020. So if you want a nice exhibition of the science of climate, then do go along to that. Thank you very much.